Now, Lawrence, to make inflation work, we need an inflaton field, a field with a strange potential Mexican hat thing that causes the false vacuum and the negative pressure. Now, is that just something people said, oh, we need to make inflation happen, let's invent a magical force that does this? Or is there actually some physical reason for believing there might actually be a field in the universe with the right energy and this rather weird potential?
Well, the answer to that question is yes and no. The point that you should realize is that, look, if you're a particle physicist, there's lots of things you can just invent to solve problems in cosmology. But the question is, are they well motivated? And inflation was actually developed not because people were searching for a cure for these problems. In fact, most particle physicists didn't even know these cosmological problems existed. It was motivated because, in fact, at the scale, which we now may have measured gravitational waves at that scale, we think the forces and the three non-gravitational forces in physics come together into what's called a grand unified theory. And it was thinking about the physics of grand unified theories that led Alan Guth originally to realize that one of the consequences might be inflation. So in fact, it's extremely well motivated. The idea of spontaneous symmetry breaking and the fact that there may be some field in the universe that gets some expectation value, that has some magnitude and visible field throughout all of nature, may sound very strange. But again, that's now on better footing than it was before as well, because 2 years ago at the Large Hadron Collider in Geneva, we discovered the Higgs particle. And the Higgs particle is related to a field that was predicted to exist throughout all of empty space, that literally gives mass to the particles that make up your body, my body, Brian's body, and everything we can see in this room. It was a bold theoretical idea. We had great confidence that many people had great confidence it was true. Frankly, I thought it was a little too simple to be true. I thought nature would come up with something a little more inventive. But it's true. So there are fields that affect the characteristics of particles. And if there's a field that has energy associated with it, at very high energy, it'll affect the expansion of the universe. In fact, the acceleration of the universe that Brian discovered could be due to a field, a similar field, but one that has very, very little energy. In fact, the big puzzle for us is, if there is such a field, why is its energy so small? If there was the same phenomena happened at the grand unified scale that happens at the electroweak scale, it could maybe produce inflation. Now, let me make this clear. There's a field at the electroweak scale that gets a value in space, and what that does is cause the electromagnetic force and the weak force to suddenly start to look different. Before that, they looked identical. When that field gets its value, photons which travel through space don't interact with that field and behave massless, but the particles that convey the weak force, the so-called W and Z bosons, interact with that field and get a mass. So that's what we call spontaneous symmetry breaking, and those two forces which were once the same now look different. Now at the grand unified scale, it looks like not only does that electroweak force get unified at the scale of the Higgs particle, but it gets unified with the strong force. We can do predictions based on real calculations and measurements, and we would predict, in principle, that they come very close together and they might be unified, and a very similar phenomenon can happen. There's a big difference. So the idea of spontaneous symmetry breaking is very well founded. The scale at which inflation could happen is very well founded, and is a natural scale in particle physics. We don't just invent it to solve some cosmological problem. That's the good news. The bad news is twofold. First of all, happily for us, actually, for some reason that we don't understand, when the Higgs field gets its value throughout space, that doesn't carry any energy associated with it. If it did, if it carried an amount of energy that you'd naturally expect it to do, the expansion of the universe would have been so fast that galaxies would never have formed, and we wouldn't be here to have this discussion. We still don't understand that.
So we would have got an acceleration back a long time
We would have
ago.
got the acceleration you observed, but it would have been so great you wouldn't have ever been born to observe it. And we don't know why it has no energy. If the field that gets an expectation value at the gut scale does get the kind of energy we would expect, then you'd naturally get inflation. Okay, in principle, you'd get inflation. But there are some additional features that need to be, some wrinkles, which mean that the kind of models that produce inflation are very special. So as natural as the idea of inflation is, the models that produce it are a little fine-tuned. Here's the first aspect. One thing is that we actually can try and extrapolate the strength of the known forces if all the particles we observe are all the particles that exist, and they don't come together at a single point. You don't get grand unification. In order to get grand unification, you have to change things. And one of the things we predict is that there should be a new symmetry of nature called supersymmetry, which, if it produces particles at the scale that we might measure at the Large Hadron Collider when it turns on again in 2015, would change the nature of the ways in which the forces change. And in fact, they do all come together at a single point. That is one of the greatest motivations for thinking that supersymmetry exists. So we need something new in order to motivate having grand unification. So that something new may not exist. Okay? We don't know. That's one wrinkle. But the other wrinkle is that when this field gets an expectation value, it's involved in what's called a phase transition. And phase transitions can happen very fast. In fact, the electroweak phase transition, when it happened, when the universe was a millionth of a second old, since we now have measured its parameters, we think happened very fast. Okay? The nature of the field changes, the way the forces behave changes, nothing remarkable happens. In order for the field that makes inflation to make inflation happen, that phase transition can't happen very fast. Because if it does, all of the energy stored in empty space that would cause the acceleration of the universe gets released into particles and radiation. And of course, the whole point of inflation is that you've got to have at least 60 e-folds of expansion to explain the paradoxes we now see today in the universe. So the universe has to get stuck in this metastable state. Well, getting stuck in a metastable state is not that much a problem, but eventually inflation has to end so you and I can be here. And that means the characteristics of the model that produces inflation are somewhat fine-tuned.
So something like the shape of the Mexican
shape
hat.
of
It has
the
to be
potential.
the right flatness
It
at the
has to
top
be
and the right
flat
rolling
enough
over.
so that the field doesn't quickly fall off and release all its energy. But it can't be too flat and never release its energy, otherwise inflation doesn't end. So that's the problem is that there is no natural model that we have right now that produces inflation. If you did the simplest, most naive model that produced grand unification, it probably wouldn't produce inflation. So we're not driven. I mean, if there was a natural model, it'd be wonderful because we'd say, well, let's compare every observation to the predictions of that model. But the problem with inflation is it's well motivated as an idea. The scale is well motivated, but right now it's an idea rather than a theory, and we don't have a model, which is why we want to measure gravitational waves and other features of the universe, because it's probably the only way we'll be able to measure the particle physics. Because, we build the Large Hadron Collider to look at the Higgs particle, but to build a collider to measure the physics that's relevant at grand unification, it would have to have a diameter of something like the Earth-Moon's orbit. It's never going to happen. And so the universe may be the only way to test these ideas. So inflation is well motivated in principle, but in practice the models are a little contrived and we don't yet understand the physics. The only way we'll understand it, we theorists can come up with lots of contrived models. That's what we get paid to do, Brian would probably say. But in fact, we rely on experiment to tell us which direction is the right one, and we don't know. But one of the interesting things about inflation that's been recognized is that it doesn't have to end very effectively. One of the big problems when Alan Guth first developed inflation was how do you get it to end? Andre Linde pointed out that in fact not ending is better than ending in general, because what you can have, and in general from many inflationary models, will be so-called eternal. Because what will happen is that the field will stay in a metastable state in most places. Every now and then, for various reasons, quantum fluctuations or other processes, it'll get kicked out of that state and a phase transition will happen, and it'll produce a Friedmann-Robertson-Walker expansion, a hot Big Bang universe. And that's what presumably happened in our universe. But that's not all of space. That's just a small seed, if you wish. And if this idea is correct, most of space is still expanding exponentially. Most of what we would now call a multiverse, namely most of what is what is all of space is not our universe. Our definition of a universe has changed. In fact, that's probably a very important thing. When I was young, and maybe before Brian was born, I don't know, we used to think of the universe as being everything there was, everything there is. That definition has changed. The universe now, for theorists and I think observers, is rather that amount of space with which we will one day be able to communicate or could have communicated. Namely, it's that region that can have a causal impact to us. That's our universe. But we don't pretend that that's everything. There can be stuff outside of our universe, stuff we'll never be in contact with. If inflation is right and it's eternal, most of space is in fact outside of our universe, and most of space is still inflating. And in other regions of that eternal inflation, another universe may be popping into existence today. Another Friedman Robertson Walker expansion may be occurring this instant, and other ones could have occurred in the past, and other ones could occur in the future. That idea is fascinating because it changes our picture of what may be possible in the universe, and we'll probably get to it. It's led to a lot of speculations that some people are very uncomfortable with, particularly observers, but some of us theorists are too. But inflation, the idea that inflation is eternal is probably more likely than it isn't. It's harder to end inflation globally than it is to have it go on and just have small regions become universes. Well, I don't know if you have a question you want to ask, because I can anticipate it, but
Yes.
but one of the facets that makes it, that's also again good and bad, there's two sides of every coin, is that if you could have many universes, if inflation can end in different ways. It turns out the symmetry breaking can happen in different ways and different places. Just like ice crystals, when you form ice crystals on a window, the crystals can point in many different directions locally, and if you lived on one of those ice crystals, that one direction would be very special. In our universe, the forces of nature evolved in the way they are, but it could be in another universe, the symmetry breaking can happen in a different way, and that would mean the laws of physics are different in that universe.